Hello, this is Ji-Hyuk Lee, the first author of the paper TopSeed Learning Selection Strategies for Symbolic Execution from Scratch. This paper is accepted in the Conference 2025 International Conference on Software Engineering, ICSE. I'm really delighted to be here to present my research paper. I hope this presentation can inspire you guys to conduct research in the software testing area. Okay, let's dive into the presentation of my paper, TopSeed. As indicated in the title of my paper, this presentation covers various aspects of symbolic execution, which is a widely used and traditional software testing method. Software testing is the process of evaluating software programs with the primary goal of detecting errors and bugs cases as much as possible. For evaluating the performance of testing, we use coverage in here. If a user wants to do testing with a program, then he or she inputs the program into the software testing tool. Then this software testing tool tries to generate test cases, and we can evaluate the test cases as with coverage. Coverage is used a metric that measures how much of a program's code has been executed. But these days, the primary focus in software testing has shifted toward improving coverage performance in this testing. Because we actually believe that executing more code can increase the probability of discovering more bugs. Sometimes we say that if you improve the coverage performance about 10% more than before, then it might be the same that you found one more unique bug in the program and the testing failed. So the main objective of software testing tools, in developing software testing tools, is to generate test cases that can maximize code coverage. Among lots of software testing tools, I would like to introduce a widely used software testing method, symbolic execution. Symbolic execution is a promising software testing technique for automatic test case generation. The key concept of this technique is that it replaces program inputs or variables with symbolic variables. So that's why we call this technique symbolic execution. In this figure, when a user inputs a program into a symbolic executor, then it automatically analyzes and executes the program codes, ultimately generating test cases. And with them, we can evaluate performance using the coverage metric mentioned in the previous slide. Moreover, this method retains metadata in a structure called a state, which contains symbolic information about branch condition expressions. Let's take a look at an example here. This example looks very simple actually, because it only consists of only two if statements in here and here. Thus, maybe we can infer that it has two branch condition expressions and two integer type variables named x and y. Here, the symbolic executor does not treat these concrete value x and y, but instead as symbolic variables such as alpha and beta as shown here. When the symbolic executor encounters the first branch in line 2, it constructs an execution tree, typically represented as a binary tree. Depending on the taken path, the executor tries to fork the state into the new states like here. Maybe one of the new state is containing the alpha is less or equal to 3 condition, and the other one would be alpha is larger than 3. Next, in line 3, the executor forks the state once again in a similar manner. The resulting forked states from a conjunction of two branches, which we can call a path condition. Because here there are two branch condition expressions. The former one is here and later one is here. Then we can describe this this form of conjunction of two branch conditions in this state. So we just call here it path condition. This path condition can represent the sequence of branch conditions traversed by the state. So here, this path condition actually can tell us the sort of sequence of branch conditions like here, here, here. Finally, when the executor reaches the return statement like here, then the state highlighted in red is also terminated. When state terminated in the executor, and it begins solving the corresponding path conditions like this. In the situation to do so, it invokes a solver which handles the symbolic path condition resolution process. If the solver returns concrete values such as alpha is equal to 4 and beta is equal to 3, then the executor outputs a concrete test case accordingly. Consequently, the test case achieves a branch coverage of 2 because it successfully explores 2 branches in the example program like code 2 and code 3. Now then, let's discuss the limitations of symbolic execution. There are actually many challenges in symbolic execution research, but in this presentation, I would like to explain only one key issue. When a symbolic executor encounters a branch, such as an if statement in our previous example, it invokes an SMT solver to determine the feasibility of the state. Here, feasibility refers to whether a given state's condition can be satisfied or not. So let me explain more easily in the same example at line number 2. The initial state is forked into 2 states based on the condition involving alpha, because the symbolic executor tries to replace this concrete value x as alpha. So we can say there would be 2 more states with the corresponding conditions, like alpha is larger than 3. But actually, before forking in this process, the executor calls the SMT solver to verify the feasibility of these 2 states. So maybe the SMT solver will return the result as satisfiable because alpha is larger than 3 and alpha is less or equal to 3 are very simple equation. But actually, if the feasible check result is false, the executor skips the fork process since it cannot explore the corresponding code area of the program. Now, then we can consider a situation where the state encounters very complex conditions like this. Naturally, waiting for the solver to return a result can be extremely time-consuming, or it may even be infeasible. A researcher proposed a very interesting result demonstrating that solver calls can account for about over 80% of the total execution time, depending on the program. This result is really interesting because we can say this is an enormous waste of computational resources. So this issue prevents the symbolic executor from utilizing the testing budget efficiently. We can call this problem constraint solving problem. And this is what I want to introduce about one of the problem in symbolic execution. Then for addressing this problem, constraint solving problem, then one approach to mitigating this problem is seeding. Seeding is a technique that utilizes previously generated test cases as seed inputs for the symbolic executor, as illustrated here. So user inputs a program with a seed in this symbolic executor, then we can call this process seeding. Then now let's consider what happens if we use a test case from the previous example as a seed. Interestingly, whenever the executor encounters a branch while using a seed, it allows to skip SMT solver calls at every branch statement. Ultimately, the executor regenerates the seed test case. At this point, I would like to share another advantage of using seed. Seeding can enable the executor to begin the testing process with forked states like here, highlighted in blue, during seed regeneration. After regeneration of the state like here, I'm highlighted in red, then these forked states serve as the initial state set. Because when the symbol executor starts to search a state without any seed, then it has to start at this entry point. But in this time, we also use seed, and we also use very knowledgeable things like this state set. So the symbol executor with a seed can facilitate targeted exploration. As a result, if a well-chosen seed test case is used, the executor is more likely to explore previous unexplored areas. This is a key hypothesis of my research. This process also prunes states unrelated to seed regeneration. In this figure, you can see that the state set is significantly simplified after seed regenerations. You can see these parts are pruned in this situation. Then we can make our symbol executor much smarter than before. Seeding is a fascinating concept, and from this slide, I would like to summarize prior research on seeding from a functional perspective. Many researchers have focused on developing new symbol execution techniques without considering seeding. So, for example, ClearArray or Homey, Lurch, FitMaker was trying to address the traditional problem like state explosion problem, but actually they didn't consider the technique with seeding. So that's why we start to do this research, because a lot of existing works didn't consider seeding. Even when seeding was used, like these papers, most approaches relied on predefined seed set rather than dynamically selecting optimal seeds. These led me to ask, what if we systematically determine the best seed test cases from scratch? Then we don't need to make our best predefined seed set, because using predefined seed set sometimes prevents from customizing our technique to the arbitrary program, because we don't know the best predefined seed set from in that program. So, and additionally, I wondered, what if we integrate our new algorithm with existing techniques that do not utilizing seed? Then maybe we can achieve even better results. So that's the point where we start to do this research. So before diving into the details, I would like to show the potential of the seeding method. I think the simplest way to select a seed test case from the generated test cases is maybe through random sampling. So we conducted an experiment using this approach, which we refer to as random seeding or RAND-seed. In this experiment, we divided the total time budget into small iterations because we want to select a lot of seeds in this process. After each iteration, we collected all generated test cases like here and stored them in a seed candidate set. Actually, these seed is basically generated test case. Then one seed was randomly selected from this set, and testing is re-executed with the chosen seed. But however, we finally found out very interesting research. It was the number of seed candidates was extremely large, approximating about 18K on average, making it very difficult to identify the most promising test case in here. Consequently, the goal of our research is to develop a method for selecting the optimal seed test case while maximizing symbolic execution performance by reducing the best number of seed candidates. That's why we try to make our algorithm TopSeed. To do so, we propose a novel seed selection technique called TopSeed, which consists of 3 key steps: data gathering, seed selecting, and distribution learning. In this overview, we can say that each time the Symbolic executor runs, it gives generated inputs to our algorithm TopSeed. Through a complicated process, TopSeed selects and returns the best potential seed to the executor again. Then Symbolic executor re-executes, rerun, and maybe Symbolic executor returns input again. And this iteration will be repeated through the total time budget. Then we ultimately obtain the final set of test cases which we evaluate based on branch coverage. Then I would like to explain my algorithm more deeply. In the first stage, is data gathering stage, we extract usable information from the generated inputs, such as coverage or the thing is like whether triggering bug or not. Actually, this is the most simple stage in this algorithm. Based on this information, we move to the next stage, seed selecting. Here, seeds are selected using 2 strategies named exploration or exploitation. Maybe you can see here 2 stages are included in here. Exploration strategy refers to selecting and delivering previously unused seed test cases from the generated seed candidates. On the other hand, exploitation involves reusing previously selected seeds from exploration by choosing high-performing test cases as new seed test cases. TopSeed determines which strategy to use based on the probability eta r. Then let me explain more deeply about exploration strategy. The goal of the stage exploration is to select seeds from unused seed candidates, requiring an evaluation of their potential, even though we've never used this test case before. To achieve this, TopSeed first converts the branch conditions covered by each generated test cases into a set. And then it performs a grouping process, clustering test cases with the same branch condition sets. If the branch condition set of test case 1 and 2 are the same, then we can make one group for these 2 test cases because these 2 test cases share the common branch condition set like this. In the next step, each group undergoes a scoring process to evaluate its potential numerically. For this, TopSeed extracts a feature vector consisting of 5 numerical values of each group. So we can extract 5 real value from this branch condition set. Actually, these 5 features are made very manually, such as group size or branch size or number of the bugs these test cases found. After this extraction stage, then TopSeed samples a 5-dimensional weight vector and multiplies it with each group's feature vector. Then we can make one single real value of each group. This allows us to represent each group with only one real number score, which is then used to rank them easily. Then, if the red group was the best group, then we have to identify the best seed inside this group too, because it still contains a lot of seed test cases. So we need to further refine the selection by choosing the best test case within the group using a extra policy. Here, a policy refers to a selection criterion based on the path condition information of each test case. For example, one policy selects the test case with the largest path condition set within the group. Anyway, after grouping the test cases, scoring the groups, and selecting a seed using an extra policy, then the selected seed is delivered to the next Symbolic execution iteration. This entire process constitutes the exploration phase of the seed selecting stage. Next one is the exploitation phase, where previously used seed test cases are reused. Maybe you might wonder why we would reuse test cases from exploration instead of selecting new ones. So actually, while developing TopSeed algorithm, we conducted a lot of experiments, and the countless results led us to incorporate this exploitation process. The first key observation was that high-performing seeds continued to significantly improve performance even when reused. We tested reusing seeds that had previously led to substantial performance gains, performance improvement in TopSeed, and the results confirmed their continued effectiveness. A good seed is one that enhances performance by guiding execution toward previously unexplored code area. In other words, a good seed expands the execution tree into unexplored areas. This means that even when reused, a good seed can help explore a wider range of previously unexplored code area. We can say it also give us higher probability to new area. And one more observation was bad seeds are less efficient when reused. It looks really similar to this first observation. Anyway, seeds without any contribution shows very low benefit upon reuse. So maybe we can say bad seed is already used for exploring area, so it can not give us higher probability to new area because it already explored all areas with this seed, because that's why we can say this seed bad seed. So it's like a lowering chance of performance improvement. And furthermore, actually, the evaluation can be based on the coverage because we already used this seed in the previous iteration. So it's really easy and simple to evaluate this seed because, in the exploration stage, we have to find out the score function or the method for evaluating the seed test case that have never used before. But in this case, we already used this seed, so we can evaluate this test case very easily. So if we can identify good seeds and bad seeds, then they may still contribute to improvement. That's the point where we would like to use exploitation stage. And in this stage, we TopSeed try to classify the used seed test case into good and bad seed. So TopSeed evaluates each seed based on the branch condition set, branch coverage. A seed receives a higher score if it explores a larger branch condition set, and if the branches it covers were not explored by other seed test cases. Uniqueness. So we can make score of each used seed based on these values when TopSeed applies k-means clustering to classify a seed into a good cluster and a bad cluster. In this stage, selecting the good cluster is similar to selecting the best group in the exploration phase. And also, we need to find out the most potential used seed test case in this good cluster. Its process looks very similar to the situation where we needed to find out the most potential seed test case in the good group. So to extract the best seed from this good cluster, we apply the same policy used in the exploration phase to select the best used seed. And the final stage of our algorithm TopSeed is distribution learning. In our algorithm, TopSeed utilizes two distributions. The first one is used to sample the weight vector for making score of each group, which is applied to the feature vector of the best group in the exploration phase. And the second distribution is the policy distribution, which is used to select a best seed from the best group or good cluster. So the weight vector distribution is updated as a normal distribution because it extracts a 5-dimensional real value vector to optimize its selection process. Meanwhile, the policy distribution is updated as a discrete probability distribution, increasing the probability of selecting policies that have previously led to high-performing seeds. So until now, I explained the main section of TopSeed in here. So from this slide, let me present the experimental results of our technique TopSeed. First of all, I would like to mention that we implemented TopSeed on the top of CLI, and CLI is a widely used tool for automatically generating test cases in Symbolic execution. And total time budget for our experiment is set to 10 hours, which is equivalent to 36,000 seconds. And the small budget, meaning the budget allocated for a single iteration and single iteration with a single seed, is set to 120 seconds. This value will be reused later as a hyperparameter discussion. In our paper, we utilized 3 state-of-the-art symbolic execution techniques to address existing challenges. Large proposed in CCS 21 and Homey introduced in FSE 2020 and Clear Array proposed in ISTA 2017. And furthermore, for a more comprehensive evaluation, we compared our technique's performance with 2 additional baselines. Original one without any seeding approach and random seeding, which I previously mentioned in the motivation slide, randomly sampled the one seed from the seed candidate set. And last comparison target is our own technique TopSeed. We evaluated all performance across totally 17 benchmark programs described in this table. And this table provides basic information about each program. These programs actually were also used in the baseline papers like Large or Homey or Clear Array. Here is the main result of our paper. It may be challenging to grasp all the details due to the small text size. To sum up the results, TopSeed outperformed all baselines, including generic CLI, Large, Homey, and Clear Array 2, under the base setting. Our technique ultimately improved performance by approximately 35.5%. It's a remarkable result. Moreover, TopSeed also demonstrated significant improvements over all baselines in the random seeding setting too. So we can say it gave 25.4% improvement over all baselines. So our algorithm TopSeed improved branch coverage significantly across all benchmarks we used. There are a lot of interesting points in this main result. There were a few cases where performance decreased despite the seeding approach. More specifically, this occurred in the program diff when compared with basically and in SQLite program when using Homey. As you can see, the performance of random seed is lower than base. So we can say even though using seeding approach, maybe the result would be worse than before. So we have to consider the selecting process of seed. So this result highlights the importance of selecting an optimal seed. So it essentially suggests that using a randomly selected seed can sometimes degrade testing performance rather than enhance it. Maybe this confirms that the importance of good seed. Additionally, we evaluated the bug finding capability of our technique, given that the primary goal of symbol execution is to detect as many bugs as possible. TopSeed successfully detected all known bugs reported in the baseline techniques. Furthermore, when combined with Homey, our technique discovered 2 additional unique bugs. And also we reported all bugs we found in this TopSeed, and we received the confirmation mail. We also investigated the influence of integrating our technique with other baselines. First, we wanted to assess the stability of our technique's performance across different settings. To do so, we analyzed the standard deviation of our results. We reported the average coverage after 5 repeated runs under the same settings and on the same programs, so we can assess the standard deviation value, like here. As you can see, random setting exhibited the most unstable performance because the standard deviation value is the highest in here. This confirms that applying TopSeed to any existing technique can enhance both performance and stability too. And in the next slide, I would like to discuss the evaluation study of our paper, discussion. The first topic of the discussion is the generality of our technique. Since TopSeed aims to improve symbolic execution by maximizing branch coverage, it can be integrated with any existing symbolic execution technique. To demonstrate this generality, we integrated TopSeed with CREST, a concurrent testing tool. Although CREST primarily employs a different approach, it still processes input as test cases, making it a suitable candidate for our technique. Interestingly, implementing TopSeed on a CREST-based technique also led to higher performance than using CREST alone. These results can confirm that TopSeed is a novel technique that can be applied to any symbolic execution tool. And the final discussion topic is the distribution learning process. We sought to analyze learning trends to determine whether any specific patterns emerged during this learning process. Actually, as a result, we identified 2 interesting tendencies. Regarding the second feature, the weight values shifted toward negative value in the programs SQLite and diff. However, for the third feature, no significant differences were observed. So we can say this observation underscores the importance of learning because different benchmarks have different trend of learning process, and this result is highlighting the importance of learning process. As with the distribution learning, we also analyze the learning tendency of the policy distribution. Also, we can find out the different benchmarks have different trend of learning policy process too. So TopSeed effectively customized weight values and probability distribution to maximize performance. Okay, in conclusion, seeding facilitates test case regeneration, reduces solver calls during state reinitialization, and serves as prior knowledge for subsequent searches. However, selecting the optimal seed remains a challenge due to the overwhelming number of seed candidates. For addressing this problem, we propose a novel technique for identifying the most effective seed test cases from scratch. As a result, our approach achieved a 35.5% performance improvement over baselines and demonstrated the efficiency of our methodology throughout the process. This is the end of my presentation. Thank you very much for your attention. I hope you found this presentation informative, and I look forward to seeing you again for an even more refined discussion. Thank you so much.